Please sit. Let's start. So, it's my pleasure to introduce the second lecture of the mini course Transversality Method and Applications by Bárány. Please.
Thank you very much. So last time we proved and take a look at the precursor of the transversality method. And today I would like to talk about what kind of applications the transversality method had, what kind of new, hopefully, what kind of, I will spoke about hopefully also what kind of new results are there which are now not relying on the transversality method, but also other results which are still relying on that, but are very recent. So, and in one case where this method began to be applied very effectively was the case of iterated function systems. So what is a basic IFS? So from now on, we will live on the real line, okay? So we have a finite index, and for every I, let us have a nice C1 plus alpha self-map on the real map on the real line, which is a contraction. Okay, so its derivative is uniformly separated away from 1, and I also like my derivatives to be also separated away from 0, so I also like to have invertible maps, and this should hold for every x. Okay, so under this case, Hutchinson has this well-known result which says that there exists a unique non-empty compact set which is invariant with respect to these maps altogether. So non-empty compact, non-compact, no, it's not good. So non-empty and compact set of R, which is invariant. Okay, it's very easy to think why there is such kind of guy, because basically because all of the maps are uniformly contracting, you can choose a big closed ball which is mapped into itself by all the sets. So there exists some B closed ball which is mapped by all the maps into itself. And then you can construct this set actually by taking a look on every possible iterates of the maps of this ball. So B was closed. This is a compact set. It's shrinking. And then take the intersection, and this set will be clearly invariant. Then the uniqueness is homework. Okay, and this is why, because you can construct this attractor by taking all the iterates. This is here, from this comes the name iterated function system. Okay, so what we try to understand now is what can we say about the dimension of this object, and especially the measures who are living on that object. So what, of course, this is a general compact set. There's a huge family of measures living there. But for us, the most interesting measures will be the dynamically invariant measures. What do I mean by dynamically invariant measures? So observe that in that set X, every point can be associated with an infinite coding. What do I mean by that? So take sigma as the set of infinite sequences formed by this finite symbol set A. And if you follow your iterations only along this orbit, I1, In, right, where I is some finite, some infinite word from the sigma, then that intersection there will be only one point. So this set is a singleton. And this is how we can define a projection from that sigma space, what we like to call symbolic space, to the attractor. Namely, you define a map pi from sigma to the reals, actually only to x, which is called the natural projection, such that pi of I is exactly an equivalent formalization, again because of the uniform contraction, the limit as n goes to infinity, fi1, fin composition at 0, where this is my infinite sequence. And this map is also is a very nice map because it's Hölder continuous. If I'm saying Hölder continuous, then I would need a metric, right? Because on the real line, there is a natural metric, the Euclidean one. And what is the metric on sigma? Well, the natural metric, or usually, I shouldn't say the natural metric because the nature depends on something. The most common metric on sigma is the following. So for I and j different words, let's consider the I wedge j absolute value as the length of the common part. So this is the smallest n such that in and jn differs. So the first position where they different, and I subtract -1 because if they differ at the first position, I would like to say that the common part has length 0. Okay? And what shall be then the common part of I and j? The first I, j many symbols of the sequence I, and if it's 0, then, I mean the length, the common part's length is 0, then I simply consider this one as an empty word. Okay? So this is some finite word, which is coming from every possible finite length word. Okay, so for this, the natural metric is usually the following. The distance of I and j is 2 to the power minus the length of the common part of I and j. And of course, if I and j are the same, then this minimum is infinite. So let's consider the distance to be 0. Okay, so in this regard, this pi map is Hölder continuous, right? Because if I'm looking at the difference of pi I and pi j, then what is it? Then basically, using the definition here, I have some common part, right? fi1, fin applied over, and one more definition. Let sigma be the left shift, the usual left shift on my symbolic space. So I erase the first character and then shift everything one position in front. So what do I see here? Sigma, that the common part, minus the same composition, the common part, shifted out the common part. Okay? And up to some uniform constants, this is what? This is, let's say, the composition of the functions fi1, again up to the common part. This should be also up to the common part. So the composition of the function until the common part, its derivative where? Doesn't matter. I like to consider it at this pi I j sigma times what? The difference of these not shifted out guys. Okay, and because these are elements of the attractor, this distance is at most the diameter of my set X, And what is this guy? Well, basically, this guy is at most gamma to the power the length of the common part, right? Again, I forgot about the absolute value, but this is gamma 1 to the power the length of the common part. And with respect to this natural metric, it's easy to see that it's indeed Hölder continuous. So when can we calculate the Hausdorff dimension of this set X? And oh yeah, the moral of the story why I told you this natural projection. Because our symbolic space or shift space is equipped with many, many regular user-friendly measures who are the ergodic measures. So what I want to do is to push forward. So let mu be sigma invariant and ergodic. And what I do is that I push forward this measure onto this set X in a usual way by using these natural projection. And I would like to understand what is the dimension of these ergodic measures. Okay, this is my goal now.
So you're not assuming any preventing overlapping?
Well, that's the point of the whole talk, that's how to handle that evil case. Because, as you pointed out, if there is no evil case, so for example, we are in the nicest case what we can imagine, namely if the strong separation holds, SSC for short, which means that for every different indices, the images of this attractor are disjoint, then this calculation is very easy. Because you can find then a uniform delta value because of the compactness in such a way that whenever you are looking at any point's tiny neighborhood, which neighborhood I would prefer, let's say the derivative of I, the word I up to n, and I again introducing notations without telling you what this notation is. So for a finite word I, let me write fi being the proper being the proper composition of the functions in that order. Okay? So the derivative at here, and I'm looking at which parts of this ball can meet with the set X. And I put here this little tiny delta. So what I expect here is that this guy, because of this, is more or less what? Is more or less the diameter of the cylinder set, the image of the cylinder set from the symbolic space via this pi map. So what I expect here, that this value without the delta would be more or less the diameter of the cylinder set of the first n coordinates of I, right? The cylinder set is all the infinite sequences who has these specific symbols, coordinates, right? So it's using the Hölder continuity property. This is basically contained exactly in this set. But on the other hand, since my delta is tiny, this is the goal of this tiny delta, that this guy here, this intersection here, this is the goal of the delta. Because if I choose delta to be very, very small, then this guy really can intersect only this cylinder set. And vice versa, if you forget about this delta from here, then this intersection will contain this cylinder set. Okay, and replace delta with the Hölder constant coming from here, let's say. So this means that if under the strong separation condition, if I want to understand the dimension of this push-forward measure, how do you understand the dimensions? Via using the local dimension, right? So if I want to understand what's going on here, it's absolutely enough to understand what is going on over the symbolic space. So this is the limit as r goes to infinity, the logarithm of the measure of the ball at this pi of I at r divided by log r. And what we see is that at these scales, this coincides with more or less, up to some uniform delta constants, this cylinder, right? Then my new measure only sees this set. It gives zero mass to all other parts, right? It lives inside of this set. So basically what you get is that it is the same thing to ask what is the limit of the cylinder set, what is the measure of the cylinder set of I up to n, divided by the logarithm, what is the derivative of I n at pi sigma n I. And we are interested in only at typical points, right? Because the dimension is given by essential infimum and essential superinum. So the Shannon-Macmillan-Breiman and Birkhoff average tells us that this is equal to a constant value for mu typical value of I, mu almost every I, right, which is the entropy over the Lyapunov exponent. So this is the entropy of my measure mu, and this is the Lyapunov exponent, which has this nice integral form. Minus integral of the logarithm fi1 derivative at pi sigma I d mu. So if we have separation, then the situation is nice. Also, observe that again using, okay, no. So this mapping here is Hölder continuous with respect to this metric, right? Sorry? No. Yeah, why not? I can reduce by 3, 10 million, whatever I want. Sorry? Gamma 1. What? You can use also gamma 1, but still the best thing, yeah, why not? You can use, instead of 2, gamma 1. Sorry? It's just a metric. I just wanted to define a metric on sigma. But this gives only Hölder continuity, right? So what you get here is 2 to the power minus log gamma I over log 2. So I did not want anything, just Hölder continuity there. Because what I want is actually to change the metric here. To change the metric on the symbolic space in order to, instead of having a Hölder continuous map like here, I want something which is Lipschitz, and not only Lipschitz, but by Lipschitz as well. Namely, I can introduce the following. What was that? What's the distance? Dij, which is using the properties of phi, and this should be the absolute value. No, the infinite norm of the composition of the common part of I and j derivative. If you check this, then under the strong separation condition, this natural projection will be not only Hölder continuous, not only Lipschitz, but will be by Lipschitz. And this is why this is a natural user-friendly metric, because you can see that with respect to this metric, it's possible to calculate what is the dimension of sigma, and also every measure on the symbolic space will have that as a Hausdorff dimension. So the question is, what happens if this bi-Lipschitz property fails? Namely, we have overlaps, right? When the strong separation condition is violated. So one method to handle this is, instead of considering one particular family, because this is just like to say something reasonable about one particular family is very, very hard. Right? There are lots of things you need to handle, a lot of particular stuff. But if you are choosing a large family in some good sense, which we consider to be a parameterized family, then what you can at least expect that typically my dimension, just like in the case of Marstrand theorem, my dimension won't drop. So what do I mean by this? So let U be some nice, open, and bounded domain on RD. And for every lambda from U, let us consider a family of maps. Right? Fi, and now my functions will depend also on the parameter lambda. I will tell you in a minute how. But I always have the same amount of functions. Okay? So I want that this dependence should be regular in the following sense, that if I'm looking at the maps as a function on the reals, then this should be C1 plus alpha for every lambda coming from U. And also I want that these gamma 1 and gamma 2 and gamma 1 constants, what I had, are valid not only for every x, but also simultaneously for every x and every lambda. On the other hand, I want that these functions are changing smoothly. So what I want is that the map which maps lambda to these C1 plus alpha maps as a function from U to the set of C1 plus alpha maps, this should be also C1 plus delta. Okay, so I want really smooth thing, which means that if you look at Fi as a function of x and lambda, then they are very smooth together. Okay, and what else do I want? And basically what I want is the transversality condition. And what is this transversality condition? For such kind of parameterized family, my natural projections, right? My natural projections here will also depend on my parameter, right? But this dependence will be nice. So for pi lambda, who is the natural projection of this IFS phi lambda, what I want is that if I'm looking at the Lebesgue measure of all those parameters, such that pi lambda of I minus pi lambda of j are close to each other with some number r. When our I and j are the farthest from each other on the symbolic space, so I and j should be such that their first symbol are different. So also what we expect on the real line, that they should be also very far. But just like what we have seen in the Marstrand theorem, it might happen that they coincide, right? So what they want to see is that the measure of those sets who are coincide should be small. So this measure of parameters should be at most constant times r. And what do I want? I want that this constant is uniform, independent of the choice of I and j. And if we have this transversality condition, let me call, this is the transversality, and let me call these continuity 1 and continuity 2. Okay? And if we have this, then there is a theorem by Szymon, Solomiak, and Urbański, which says that for every new ergodic measure, ergodic shift invariant probability measure, if you are asking what is the Hausdorff dimension of the push forward of this measure onto the attractor, it is minimum of 1 over the entropy divided by the Lyapunov exponent. But again, these functions, this is the definition here of the Lyapunov exponent, somewhere it's written there, oh yes. So these functions are depending on lambda. Natural projection will depend on lambda. So the Lyapunov exponent will also depend on lambda. And this holds for almost every choice of lambda. And I also have to write there the 1, right? Because my dimension cannot exceed the state space. But also, if you are looking at the set of parameters, let's say u prime, for which this entropy over Lyapunov exponent quantity is strictly greater than 1, and it's non-empty, and it has positive measure, so actually I should write as follows, that for almost every lambda coming from this set, what you also have is that the push forward of this measure is absolutely continuous with respect to the Lebesgue. So what it means that it happens what you expect to happen, that there is no dimension drop, at least typically.
Okay, but this transversality condition seems to be very difficult to check.
And this is my next step, exactly. How to prove transversality conditions. Yes?
I don't know if this is a silly question. What the transversality comes from what do you call it?
Well,
This transversality condition.
and I will tell you also in 1 minute as well. And I will answer simultaneously for both of your questions. Exactly. Yes?
There are examples where the number dimension is 1, but it's not absolutely continuous.
Yes, there are. For example, if you choose the following system, 1/3 x, 1/3 x plus t, and 1/3 x plus, what is my favorite number? Let's say 1. Then, for Lebesgue almost every value of t, the Hausdorff dimension of the measure will be, the following measure. Which measure I'm talking about? I'm talking about the Bernoulli measure with 1/3, 1/3, 1/3 probabilities. Okay? In that case, for Lebesgue almost every t, the Hausdorff dimension of this measure will be 1, but not absolutely continuous. So for Lebesgue almost every t, this guy, if I push forward, because I have one parameter, the t translation, I push forward it has dimension of 1, but it is singular with respect to the Lebesgue measure. So in order to ensure absolute continuity, you really need this threshold. But very good question, thank you. Okay. So now what I want to show you how to check this transversality. And basically, under that smoothness conditions, what you see there, so C1 and C2, actually, to be honest, in our paper, we did only the C2 case, so C2 plus alpha and C2 plus delta, but I haven't checked it, but I'm pretty sure, so it's an exercise to disprove me or verify me that this will hold also in the C1 plus alpha regime. So basically, under these C1 and C2 continuity assumptions, the transversality holds if and only if you can find, if and only if for every I and j infinite words who are not the same, if you see that the image of these points coincide, then it must imply that if you take the derivative with respect to lambda, and by this notation I mean the gradient, right? So we are in RD, so this should be my gradient. This is positive. And this is where also the name transversality is coming from. So basically it says that if you have two different words, I and j, and this is a function of the natural projection as the parameter lambda of I, then it can only intersect transversally the natural projection of every other j. Okay? And this is basically just a simple compactness argument. So in this case, I'm not claiming that this transverse is uniform. It can be arbitrarily small if the common part is large. But if you say that already the common part is small, namely the first symbols are not the same, then you would get a uniform lower bound. Okay, this is just a very simple compactness argument. And this is where the transversality, the name, is coming from. Okay? So, yes, please?
Does it make any sense to replace this assumption by something little, just assuming like half to the power alpha?
Absolutely makes sense. But then, using that method, what you get is that you cannot handle all ergodic measures anymore. For example, if you put here the square root, which would allow, in that context, second order roots, then you won't be able to handle every ergodic measures, only ergodic measures who has dimension at most 1/2. Or also, to show the absolute continuity, the opposite direction, that who has very large dimension. Okay, so these are, so then you lose something, some threshold. I would bet that it should be. I don't know. Let me point it this way. I don't know. I think it should. Okay, so what do we get is that in order to have transversality, we need to see this transversal picture. But it still does not, it's still not easy. I did in my life several times to verify the transversality condition for certain systems. Awful. Very, very technical. So let me show you one awful proof for that. Actually, this is not an awful proof. This is a very nice proof. And basically, this is somehow what I can say that one of the most natural parameterizations. Because I have C1 plus alpha maps. How on earth, what is the natural parameterization? But the natural parameterization is using translations. Okay, so now I say my number of the functions is D. U is an open bounded domain of RD. And my parameterizations will be the translation vectors. So I fix some Fi functions from A in such a way that that they are uniformly contracting. I will tell you in a minute. So fix some C1 plus alpha contractions. And then what I claim is that phi lambda, this parameterized family of IFSs, parameterized by this translation, has transversality if you look at the maximum of different symbols and you take the derivatives, right, the contracting ratios. The sum of the two largest contracting ratio cannot exceed 1. And this is also what we have to expect if you are trying to use the transversality method. It has its boundaries. Namely, there will always come up something technical condition under which it's possible to verify, and there will be a huge region of systems which cannot be touched by using the transversality method. Okay, so there are also weaknesses. But let's see why this is true. Okay, so in that case, how does the natural projection look like? Right? From the definition, which is not on the board anymore, but we see that it was this limit definition. So what we see here, that this is exactly Fi1 of pi lambda sigma I plus the translation parameter at I1. So if I take the derivative, the partial derivative with respect to the any kind of translation parameter, right, with respect to the kth one, then what can I write? It is the derivative of the first function times the partial derivative of the image of the shift plus a direct delta, right? Which is 1 if I1 equals to k and 0 otherwise. But it also says that I can write this partial derivative of my natural projection in a nice user-friendly summation form. This n goes from 1 to infinity. I take the, oh my God, I have not enough space, so I have to migrate here. So yeah, this is the sum as n goes from 0 to infinity. The Dirac from 1 to infinity. The Dirac in, that whether my nth symbol is corresponding to this k symbol, times the composition of the functions up to the first n minus 1 coordinates, looking at its derivative, times pi lambda sigma n, I think n minus 1, yeah. So this nice summation form. And what do you want? You want that this gradient is positive, right? I take two infinite sequences, I and j, and what you want is that the gradient vector of the difference is really transversal. So what can I take? I would be happy if there exists a k such that these partial derivatives of I minus pi lambda j such that I1 not equals to J1, this is bounded away from 0. This is what I want. But using this formula, what do I see? This is equals to, well, what is the first symbol minus, what is the first symbol in J? Plus something. Plus some terms depending on K and depending on the shifts. Yes? Delta K. Oh, yes, the Dirac delta. So it's Ij, it's 1 when I equals to j, and 0 otherwise. So look at here. This guy here is either 1, minus 1, or 0. Right? So if I choose k to be either I1 or J1, then this has absolute value 1, so my only job is to show that this guy here is at most 1, or separated away from 1, for some certain choice of k. Yes? Oh, it's nothing, whatever the remainder from this formula is. But you can also use this formula for this remainder to observe that I was using gamma 1, so I should use, let's say, Ri to be the infinite norm of my contracting ratios. So this guy here, then, at most, so you're using this form. So now the first terms are here, everything else is there, and goes from 2 to infinity, actually from 1 to infinity, the first n symbols of Ri times the Dirac delta, right? Because if it's not there, then I don't give an upper bound for this. Okay? Why is it good? Oh, I need my notes, sorry. Why is it good? Because if I multiply this guy with 1 minus Rk, then what do I see here? This is basically this Dirac delta I n plus 1k, 1 minus R I n plus 1, right? This is the same. And I can further estimate it if I say that all these Dirac deltas are 1. So, and what do I get? This harmonic sum. It says that this is at most Ri1. But you have the same, right? This is true for every k. This is true for every k. So it's true for I1 and this is true for I2. So 1 minus Ri1, so Rk times absolute value of this Ek belonging to the sigma I, plus 1 minus Rk, the absolute value belonging to the sigma j, they are at most Ri1 plus Rij. And actually, I could, oh, sorry. Yeah. Oh, actually, I could have used here I1, and I should have used here J1. So it's true for every choice of k. So also in particular, if for the sigma j I choose j, and for sigma I choose I1. Okay? But on the other hand, if I choose the minimum, right? Out of I1 and J1, out of these guys, this is 1, 2 minus R I1 minus R J1, right? I have chosen here the minimum of these guys. And exactly by the condition, because what is this condition? This condition says that Ri1 plus Rj are strictly smaller than 1. We get that at least, either if I use I1 or I use J1, it will be strictly smaller than 1. So 1 plus or minus something strictly smaller than 1, this must be bounded away from 0. And this is the proof. I cannot tell you anything more enthusiastic. It's always like that. Right? You need technical effort to show transversality. But let me show you in the last, I think, 5 minutes. Am I right? Yeah. In the last 5 minutes that this effort worth to be done still. Because we know, I mean, I don't know whether you know, but there are very brand new type of methods to handle the dimension theory for iterated function systems. And then the next time I would like to talk about these two. So the recent methods of Hochmann, Shemerkin, and Rappaport, relying on additive combinatorial methods, would give you much better estimates in certain cases of IFSs. Okay, I don't want to go into the details. What I want to tell you is there is another transversality introduced by Peres and Schlag. This was the so-called beta transversality. In that setup, what we have, it means the following. So remember that we had this as the common metric on the symbolic space. Peres and Schlag said that the beta transversality holds if you are looking at these different words. So for every lambda from your parameter space, they are too close to each other. They are closer than this natural distance to the power beta. Beta, whatever, positive. Can be very, very large, can be very, very small, depends on the situation. But they claimed that then the gradient vector then should be at least that large. Okay, this is what they claimed. This is the beta transversality. I can say that, okay, if you don't want to remember for that, then you shouldn't, because what we also showed with Boris Solomiak, Károly Simon, and Adam Spiewak, that the usual transversality, I just wrote there a few minutes ago, is equivalent with the beta transversality for every beta. Your constants are changing, but it's essentially equivalent. Right? Oh, there exists a constant. This constant depends only on the beta. This is what we showed. So you have beta transversality if you have usual transversality. Why am I telling that for you? Because there is this very recent powerful result of Mung Wu, who showed the following. That if you consider the parameterized IFS, which is a linear IFS, so you parameterize IFS which contains only linear maps. This is also usually called self-similar system. In such a way that these parameterizations are C2 smooth. And what I also want is that the parameters of mine are living in an interval. Okay? So one-dimensional parameterization, contracting ratio, and translations are smoothly parameterized. So he showed that for every mu Bernoulli measure on the symbolic space, if you look at the exceptional set, those lambda values for which the Hausdorff dimension of the projection, push forward just 1 second, is strictly smaller than what it should be. What it should be? Well, 1, entropy divided by Lyapunov exponent. If you look at this set, this is at most countable. It's needless to say that it's a much, much larger set. Because previously we only have seen that the exceptional set has 0 measure, and now we see that it's only countable. It also relies on the transversality method. So there are examples where it's satisfied. For example, the Bernoulli convolutions. Right? When you have one lambda parameter between 1/2 and something 0.65, and you consider the IFS lambda x plus 1. And then what we know that is a result of Boris Solomiak, that up to this 0.65, this IFS satisfies the transversality condition. So we know that on this interval, there are only countably many exceptional sets. Also, Waryu already showed that for this system, if lambda is transcendental, then you don't have dimension drop, right? You must have, for transcendental lambda contraction ratios, you must have here equality. Okay, but also another example which can be handled is like lambda 1x, lambda 2x plus t, and lambda 3x plus 1, just by using our previous knowledge. So if you, for example, assume that all the lambda i's are strictly smaller than 1/2, then this system will be what we have seen, transversal, and where the dimension of any Bernoulli measure can drop is only happens on a countable set of these t translation parameters. Okay, so thank you very much for your attention.